In this video, we're going to learn about something called diagonalization and a special version of it called orthogonal diagonalization that you're going to be able to do to a given matrix. So we'll start with a definition here. A matrix is called diagonalizable if there's a diagonal matrix D and an invertible matrix P such that A is equal to PDP inverse. So basically we want to write the matrix that we started with A in terms of this matrix P, and especially this diagonal matrix D here. Let me give you a quick idea why we want it written in this format here. First off, if your diagonal matrix is like say A0, 0B, and you want to raise that to a power, all you have to do is raise the individual diagonal elements to the power. So finding powers of diagonal matrices is really easy. However, if you have a matrix that is not diagonal and you want to take it to the fifth power, it's going to be a gigantic pain because we can't do any shortcuts here. We have to write it out 5 times and then just keep doing all those matrix multiplications. However, if I can write my matrix A as PDP inverse, and I want to take A to the fifth power, now first things first, I cannot just distribute that exponent in. The algebra of matrices doesn't work that way. I have to just write it out 5 times. And so on. And something kind of magical is going to happen. All the inner ones, P inverse times P, are going to cancel out. And what you're going to be left with is just P, and then all 5 of the D's you had, and then one last P inverse. So it's P D to the fifth P inverse. And we just saw that taking diagonal to a power is really easy. And so what this does is this allows us to go ahead and take powers of matrices in a much easier fashion as long as we diagonalize the matrix first. And in fact, there's something really not part of what we're doing here, but there's also a way that you can take E and raise it, or any other number, and raise it to the matrix A. So in order to do that, though, you need to have the diagonalization for the matrix A. So this diagonalization idea here, we're going to see it for a couple of small applications, but in the future, that's going to be used in several other applications when you get to higher level classes. Before I give an example, though, I want to make a little point here. Not every matrix is going to be diagonalizable. Some are and some aren't. There are some theorems that can help you determine whether something is diagonalizable. On the other hand, when I give you a problem and I ask you to diagonalize something, well, it's going to be diagonalizable because otherwise I wouldn't have asked you in the first place. And when you start taking just random matrices, most likely it is going to do it. But regardless, this is what we have here. So the way we're going to diagonalize the matrix is you're going to find the eigenvalues and eigenvectors. Well, for the matrix 1, 2, 2, 1, in the previous video we actually already found them. So I'm going to skip some work right now. And we're going to do lambda is 3 and eigenvectors 1, 1. And lambda is -1 with eigenvector -1, 1. And if you don't like skipping the work, you have to do determinant of A minus lambda I, set it equal to 0. That's where you get your 2 lambdas. Then once you have your lambdas, you're going to try to find the null space of A minus lambda I. So just a reminder of how that works, but if you're not sure, take a look at the video that we had before on finding eigenvalues and eigenvectors, and you'll see this exact example. And the great thing now is that once we have our eigenvalues and eigenvectors, once we have these things, we're done. All we have to do then is, for our diagonal matrix, put down your two eigenvalues, which are 3 and -1. And for your P matrix, just put down your two eigenvectors and make sure you put them in the right column. So the number 3, the eigenvalue 3 was in the first column, so that means the eigenvector for 3 should be in the first column here, and similarly for the second column being for lambda is -1. And so this is it. Once we have that, then we can write down our matrix A, 1, 2, 2, 1, as this matrix P times this matrix D times P inverse, which we could work out if we really needed to. And there you go. There's the diagonalization for this matrix. So really, diagonalization is not that much more work. It's all coming down to, can you find the eigenvalues and eigenvectors? And if so, it's just one more step where you put them into P and D. That's all you have to do here. Now, for the second part of this, we're going to look at something called orthogonal diagonalization. And what that means is, first off, the matrix being orthogonal itself is that when you take the inverse of a matrix, you're going to have the same thing as the transpose. So if you take a matrix and you take the inverse of it, and it works out to be the same as the original transpose of the matrix, we call that an orthogonal matrix. Well, not all matrices are going to have that. In fact, not that many of them. But if you can find not just any P, but specifically an orthogonal matrix P, and again a diagonal matrix D, if you can write it in this way, then we call the matrix not just diagonalizable, but orthogonally diagonalizable. It turns out there's actually a really easy condition to check whether something's going to be orthogonally diagonalizable or not, and that's just whether the matrix is symmetric. And in case you've forgotten what symmetric is, that's when you take the matrix and transpose it and get it back to itself. So for our example here, 1, 2, 2, 1, if you transpose that, it's still 1, 2, 2, 1. So that's an example of a symmetric matrix. And again, every symmetric matrix is going to be diagonalizable. And if it's not symmetric, it is not going to be diagonalizable for us. Okay? Now, how do we actually find the diagonalization that's orthogonal for this? Well, it turns out is that you just modify one small thing. So we already have our eigenvalues and eigenvectors. They were lambda is 3 with eigenvector 1, 1, and lambda is -1 with eigenvector -1, 1. And we're going to create our D matrix the same way, 3, 0, 0, -1. And the only difference here is that when I make my P matrix, instead of just copying down the eigenvectors, I'm going to turn the eigenvectors into unit vectors and then put them in. So if I want to make 1, 1 into a unit vector, I divide by its length, which is going to be √2. And that's all I'm going to do. Put this 1 over √2, 1 over √2. And the second one's going to become -1 over √2, +1 over √2. And then you can double check that this is in fact an orthogonal matrix P. And if that's the case, then you can write your matrix A as my P, D, P transpose. And this would be the orthogonal diagonalization for this matrix. So there's general diagonalization that works on a lot of matrices, but not all of them. And then there's this special version called orthogonal diagonalization that only works specifically on symmetric matrices, but it gives you a stronger property than the one we had in the first case, the regular diagonalization.